Hello and welcome to Sean White's Solar and Energy Storage Podcast. In this podcast, we are going to talk about the 2023 National Electrical Code. To be more specific, we're going for Part 4 of Article 690. As we have already talked about Parts 1, 2, and 3 of the 2023 National Electrical Code, Article 690. And this is something that I have been doing for many years. I believe I started reciting the National Electrical Code like poetry when it came out. I think the first version I did this for was the 2008 National Electrical Code, way before I had a podcast. And I just posted it on my website. I called it Radio 690. And by the way, I used to be a DJ on the radio at KHNS, Haines, Alaska. But I wasn't talking about the NEC there. I was spinning vinyl. Yes, they still have vinyl in Alaska. I actually donated all my records there. So what I've been doing as I've been reciting this is I've been going right off of the words of the National Electrical Code, but in order to celebrate the release of our book, PV and the NEC 3rd edition by Sean White and Bill Brooks, based on the 2023 National Electrical Code, I am going to read it from the book. So the book, maybe someplace should adopt the book instead of adopting the National Electrical Code. If you're one of those AHJs, I dare you to adopt PV and the NEC. I've actually heard that some people have taken our book to the inspectors and passed inspections based on our book. What do you know? That's pretty cool. So kind of just think of this as an audiobook. And if this is a little bit over your head, you can kind of absorb some of the language, some of the things that we're talking about. Things will become familiar. It'll get into your subconscious, that part of your brain that you don't know that you use. You're using it. You're absorbing this stuff. And so here it is, Chapter 5 of the 3rd edition of PV and the NEC by Sean White and Bill Brooks, which is Article 690, Part 4, Wiring Methods and Materials. Article 690, Part 4, and by the way, too, they make it IV for 4, not as in the IV curve. Part 4, Wiring Methods and Materials, covers the methods and materials specific to wiring PV systems. Much of this material refers to and works with other articles in the NEC, especially the NEC articles within Chapter 3, Wiring Methods and Materials, such as Article 310, Conductors for General Wiring. Now we have a text box here, which is like commentary. Chapters 5 to 7 modify the first 4 chapters of the NEC. This means that if there is a difference between the regular wiring methods and Article 690, when we are dealing with a PV system, we will go with Article 690. Same would also go for articles in Chapter 7, such as 706 Energy Storage Systems, which modifies the first 4 chapters, including Article 480 Storage Batteries. If Article 690 does not tell us to do something special, then we will use the methods found in Chapters 1 through 4. For example, with AC inverter circuits inside of a house, we can use NMC cable, that's Romex. And for DC PV circuits on a rooftop, we can use PVC, since the requirements to be in metal are for PV DC circuits inside of a building. A lot of people don't know that. And now we are out of the text box. The commentary. But sometimes I just can't help it myself, and I throw in some commentary like this commentary right here. That's podcast commentary for you. Although there are PV specific wiring methods in 690 Part 4 wiring methods, all other parts of the 2023 NEC apply to the wiring of PV systems. And then in the book itself, I do a big outline of everything that's in the NEC, so I'm not just going to read this outline. And then what I have here in this chapter is an outline, and it has all the order of all the things, because it gets kind of confusing when you have the NEC divided into different things, such as chapters, like Chapter 6, which Article 690 is in. Then we have Article 690. So we have articles. Then we have sections, which are parts of the parts. So for example, we have Part 4, Wiring Methods and Materials. Then we would call it section 690.31. So then you call it a section. And then the sections are divided up to, we have 690.31A, then we have 690.31A1, Then we have 690.31A31, and you can see how it can just go into super detail. So we have a couple of pages here just dividing all this stuff up. And just for your purposes, for you listeners out there, just know that the NEC, which is also called NFPA 70 for National Fire Protection Association, and then the 70 is the number of what they call the NEC. They have a whole lot of different codes and standards, the NEC being the most popular one. And then we are breaking it into chapters, like we just talked about. Chapters 1 through 4 apply to everything. And then inside of chapter 6, we have Article 690. It starts with a 6 because it's in chapter 6. And then inside of these chapters, we have parts. They do Roman numerals there, so it's IV for 4. And then we break that down into sections, and we even break down those sections. And so it gets kind of confusing, and it's nice to just be able to look at a nice outline. Okay, so the next part of the chapter of this book is 690.31 wiring methods. It is amusing when we see 690 Part 4 wiring methods and materials, then it's 690.31 wiring methods, then it's 690.31A wiring systems. We see a lot of repetition that emphasizes the importance of our wiring methods and material systems. Ah ha ha! Those NEC writers, they are so funny. I think the NEC should win like some kind of comedy Emmy. And now we have 690.31A wiring systems, and that is broken down into 690.31A1 serviceability. Sufficient length of cable shall be provided in enclosures for replacement. Discussion. Since your inverters and equipment will likely be replaced at some point, we need to make it easy for that future person who may be your future self with a different set of atoms. Like, did you know that? That your atoms keep on changing? That a year later, almost none of you is the same? It's just some pattern that we are. Back to the book. Now we have a text box. So some more commentary, and this is referring to a different chapter, chapter 3. And so it says 300.14, length of free conductors at outlets, junctions, and switch points. Says that we need 6 inches of free conductor. It also says that for boxes measuring fewer than 8 inches in any dimension, we only need the wire to be able to extend 3 inches outside of an opening. Additionally, if the wires are not spliced in the box, then this requirement does not apply. And now we are out of the text box. 690.31A2, where readily accessible. PV-DC circuits over 30 volts in readily accessible locations shall be one of the following. 1. Guarded. 2. In MC cable. See Article 330, metal-clad cable type MC. 3. In raceway. Parentheses. Does not require metal raceway here. However, requirement for being in metal is for DC circuits inside of buildings. See 690.31D1 on page 119. We're just trying to emphasize the point there that that requirement for metal is for DC PV circuits inside of buildings, not outside of buildings, not AC circuits. People oftentimes get that mixed up, you know. 690.31A3 conductor ampacity. Ampacity, you know what that is, right? That is the ability to carry current. Table 690.31A31. It's a lot of keystrokes. 690.31A31 shall be used for correcting ambient temperatures over 30 degrees C for conductors with 105 degrees C and 125 degrees C rated insulation. The temperature rating of the insulation is theoretically how hot the wire can get after running the current in the ampacity table through it under given conditions. At this point, nobody is using 105 degrees C and 125 degrees C wire. However, Bill, co-author of the book, put this in the NEC since he is an NEC futurist and a copper cost reductionist. Yes, that's right, we have the Copper Cost Reductionist Society, and Bill is perhaps the main force putting together solar type information into the National Electrical Code. He works very hard at it. For proper wire sizing, see Chapter 12 Wire Sizing of this book. Table 690.31A31 is essentially an extension of Table 310.16, but with higher temperature rated conductors. You got that? Nobody's really using this table yet, but it's for the future. It's extending Table 310.16 if you wanted to use a conductor that's rated for super hot temperatures, like hotter than boiling. Table 690.31A31 in the 2023 NEC was Table 690.31AA and 690.31A in the 2017 NEC. Yep, lots of changes there. In the 2017 NEC, the temperature rating of the wires included temperatures covered in the 310 tables. In the 2020 and 2023 NEC, this table covers 105 degrees C and 125 degrees C insulation temperatures only, which are very hot. Perhaps we are preparing for a Venus-like climate. This is not a political statement. Gosh, man, everybody gets so uptight these days. Text box here, Table 310.15B2A, ambient temperature correction factors based on 30 degrees C, the 2017 NEC, was renamed Table 310.15B1 in the 2020 NEC, and then 310.15B11 in the 2023 NEC. The 310 tables have been seeing a lot of name changes lately, but the content remains the same. Isn't that a Led Zeppelin song? The content remains the same? Having a high school flashback here. See page 275 for details. Perhaps the code-making panel wants more attention. You know, those 310 table people are bored because physics doesn't change, and so they got to change something, so they change the name. And the content remains the same, just like the song remains the same. 690.31A3 continued. Table 690.31A32 shall be used for determining ampacities of conductors rated for 105 degrees C and 125 degrees C. This table can be viewed as an extension of the table now known as 310.16 because from the 2011 to the 2017 NEC, this table was temporarily named 310.15B16. Gosh. Although conductors with a higher temperature rating can carry more current, they will still have the same voltage drop as conductors with a lower temperature rating. Since PV prices are getting so low, at this rate, they will pay us to take it in a few more code cycles, so why not save money on smaller wire? If you do not see Bill's name on the next edition of this book, it means the copper industry has taken him out for reducing the amount of copper required on a PV system. Sean hears that overcurrent protection device manufacturers also have put a hit on him. It is dangerous writing the National Electrical Code. Careful, Bill. So then we have an image of this table, and we're showing different temperatures and temperature ratings of conductors and different derating factors. And just remember, it's kind of a future thing that we're not really even doing yet until somebody makes 105C PV wire or something like that. And then we can run our circuits through boiling water. In fact, if something is 105 degrees C, boiling water would cool it off. That is cool. Or is it? 690.31A4 special equipment. Isn't that special, Mr. Rogers? Wiring methods listed for PV systems may be used in addition to wiring methods in the code. And here we have a special text box with some commentary again. And it says permitted wiring methods. Some bullet points. Raceway wiring methods in the NEC, cable wiring methods in the NEC, other wiring systems specifically listed for PV arrays, wiring that is part of a listed system. Now it says the following are comments on different wiring systems with some more bullet points. Raceway wiring methods in the NEC, and raceway wiring methods are found primarily through Chapter 3 of the National Electrical Code. Chapter 3 is titled Wiring Methods and Materials. Kind of goes along with 690 Part 4 Wiring Methods and Materials, huh? EMT is another bullet point. EMT is often the raceway method of choice and covered in Article 358 Electrical Metallic Tubing Type EMT. And so if you are a NABCEP preparer or an electrician, somebody that wants to know about the NEC, that's something for you to remember. Article 358 EMT, 358 EMT. Got it? Say it 10 more times. Hit pause, say it 10 times. Okay, now you know it. 358 EMT. Bullet point, cable wiring methods in the NEC. Cable wiring methods are also found in Chapter 3 of the NEC. Lots of stuff there in Chapter 3, huh? That's a big chapter. USE2 is a popular cable and is covered in Article 338, Service Entrance Cable Types SE and USE. The -2 of USE denotes that it is 90C rated. So that's right. If you're going to look for USE2 cable, you look under where it says SE and USE because the -2 is just 90C rated. PV wire is another wiring method that was specifically required in the 2014 NEC, but isn't an option along with USE2/RHW2 in the 2023 NEC. I'm just going to mention too that that is a new thing in the NEC, that the USE2 cable has to be dual listed as RHW-2, which it almost always is anyway. Bullet point, other wiring systems specifically listed for PV arrays. And for instance, a cable manufacturer could design a cable that was superior to PV wire, get a certifying agency to list it, and now we have another cable listed for PV arrays. Oh, I can't wait to do that. Wiring that is part of a listed system. While this listed system could be a wiring system for rapid shutdown, it could be any special cable used as part of the listed system. The in-phase microinverter cable fits under this listed system category. And so we also have another table here on this page that comes out of the NEC, 690.31A32, ampacities of 105 and 125C rated wire, not in free air. And pretty much we just have the wire sizes and then the ampacities of these cables that are rated for 105 or 125 degrees Celsius. And did you know that 125 degrees Celsius is 257 degrees Fahrenheit? And so when water gets that hot, it is steam. It changes phases. You cannot have a hot tub that hot. I know, I've tried. I like it hot. 690.31A4 informational note. And so that's right, the NEC has these informational notes, and it says, see 110.14c temperature limitations. Under 110.14 electrical connections, or see how to do this in Chapter 12 wire sizing of this book, which is easier to understand than the NEC. That's why we wrote it. Also explained on page 44. And yes, I keep referring to Chapter 12 wire sizing because we do wire sizing examples, and wire sizing is so darn confusing that nobody can figure it out without studying it for years, and most people do it wrong. Even people that are the top experts in the world do it differently. So somebody's doing it wrong. They can't both be doing it right. And so what we did is we just put some examples in the book. And one thing that's kind of interesting about that is sometimes you can do a calculation where your overcurrent protection device has a current rating that is higher than the ampacity of your conductor. Isn't that confusing? Isn't the overcurrent protection device supposed to protect the conductor? But there's some cases where we can do this weird rounding up thing of a conductor and actually make it so our conductor has a lower ampacity than the overcurrent protection device. That does not make sense, but that's the way it is. And you have to read Chapter 12 where you can see it there. And once you understand that it doesn't make sense, then you understand. That's how you can really understand the NEC. 690.31b, identification and grouping. There was a little bit of rearranging here in the 2023 NEC, including turning things into lists. 690.31b1, conductors of different systems. Unless allowed in the important exceptions below or allowed in equipment listings, then PV circuits shall not occupy the same equipment wiring enclosure, cable, or raceway as other non-PV systems or inverter output circuits unless separated by barrier or partition. Partitions are available with some enclosure products such as gutters. Come on, get your mind out of the gutter there. Most jurisdictions will require a partition to be an accessory included in the listing of the enclosure. 690.31b1 exception. Sometimes the exception is more common than the rule. If all conductors and cables have an insulation voltage rating that is at least that of the highest maximum circuit voltage, that's 690.7a defines the maximum circuit voltage, then the following 1, 2, and 3 shall be permitted. So we have 690.31b11, power limited circuits. Multi-conductor jacketed cables for remote control signaling or power limited circuits are permitted in the same enclosure cable raceway as PV DC circuits, assuming all circuits serve the PV system. Discussion. And this is common, so some of you might want to pay attention here. Common topic for people. Discussion. Think of this as your data rapid shutdown signaling and CT cables. You just need to make sure the insulation is rated for the higher voltage. 1500 volt Cat5 network cables are available, by the way. Example, if there is a 600 volt circuit and a 24 volt circuit in the same jacketed cable raceway enclosure, then the insulation around the 24 volt circuit has to be rated for at least 600 volts. 690.31b12 inverter output circuits. Inverter output circuits, that's AC, can occupy the same box or wireway as PV DC circuits that are identified and grouped, which is required anyway according to 690.31b2 identification and 690.31b3 grouping, and coming right up. Discussion. Since identification and grouping is already required, then we almost do not need to mention grouping in identification. Can you identify with that? 690.31b13 inverter output circuits and non-PV systems. DC circuits using multi-conductor jacketed cables, MC cable, or listed wiring harnesses that are identified for the application and permitted to occupy the same wiring method as the inverter output circuits and non-PV systems. Discussion. Here we can even combine non-PV circuits in the same wiring method. So as we said, the exception is more of a rule. 690.31b also tells us we need to comply with both 690.31b1 identification and grouping and 690.31b2 grouping. You know, if you really want to study this stuff, you might have to repeat it a few times. Some of this stuff is pretty complicated. You might have to read the book. Get the book. Get it on Amazon. It's easy. Be on your doorstep tomorrow. 690.31b2 identification. PV system DC circuit conductors shall be identified at accessible points of, bullet points, termination, connection, splices, and there's an exception. If evident by spacing or arrangement, further identification is not required. That's nice. We can color code things. Maybe we could use some nail polish. You know, there's all kinds of electricians out there. Means of identifying PV system circuit conductors. Color coding, marking tape, tagging, probably not spray painted gang tagging, but it doesn't say you can't, homie. Other approved means in 690.31b2a and B coming right up. 690.31b2a, other approved means of identification. Can we use Braille? I don't know. Using color for polarity identification shall be done with a permanent method such as bullet points, labeling, sleeving, shrink tubing. 690.31b2b, and one other approved means of identification. Non-solidly grounded positive conductors shall include either imprinted plus sign or the word positive or POS, durably marked and not green, white, or gray. So it doesn't say it has to be red, it just says it has to have a plus or a positive or a POS on it. I'm voting for plus. Takes less effort and it's a little bit more Christian. Non-solidly grounded negative conductors shall include either imprinted negative sign, that's a hyphen pretty much, the word negative or neg. I wouldn't write negative on it, it's just I'm too much of a positive person. Durably marked and not red, green, white, or gray. So negative can't be red, but positive doesn't have to be red. Whoa. Note, only solidly grounded conductors shall be marked in accordance with 200.6 means of identifying grounded conductors, which is where you find white wire for the neutral rule and alternatives such as gray. Discussion. Solidly grounded systems in the 2023 NEC that's 2017 NEC and after, are rare systems that are not fuse grounded. An example of a solidly grounded PV system, according to the 2023 NEC, is a direct PV well pump where the negative conductor is solidly connected to the grounding system that includes a grounding electrode, often a well casing. Grounding through a fuse is not solidly grounding. So those people in the 2014 NEC and earlier, they had it all wrong. It wasn't my fault, I swear. Darn fuse grounders, thinking that they're really solidly grounded. Whoever invented that system's probably blowing a fuse right now. These rare and solidly grounded conductors will most likely be marked white according to 200.6. The marking could be gray, 3 white stripes, or 3 gray stripes, if you want to be creative. Fuse-grounded current-carrying conductors that operate at 0 volts to ground are not considered to be meeting the requirements of 200.6 and should not be identified as white as they were in the 2014 NEC and earlier versions. The AC side of the inverter is most often solidly grounded, just like anything else AC, like the upper right prong on that plug in your wall. The 690.31b2 identification exception tells us that if the identification of conductors is evident by spacing or arrangement, that we do not need other forms of identification. 690.31b3 grouping. If the AC and DC conductors of a PV system occupy the same bullet points junction box or pull box or wireway, then the AC and DC conductors of each system shall be grouped separately by cable ties or similar every 6 feet. If you're 6 feet tall, it's kind of easy. You just lie down there, mark it with a cable tie, wrap it around those wires. The 690.31b3 grouping exception tells us that the grouping does not apply if the circuit enters from a cable or raceway that is unique and obvious. Parentheses, what is obvious to a qualified person is oblivious to someone who has not yet read this book. Play of words. You could really tell that our book is published in the UK, where William Shakespeare is from, even though it's on the National Electrical Code. And that's the truth. 690.31c cables. PV wire or cable and distributed generation DG cable shall be listed. The PV wire listing is UL 4703 and the DG cable is UL 3003. And now we're going for a text box. UL listing numbers in this industry are related. The UL listing for PV is UL 1703 or 61730 more recently, see below. If you change the 03 to a 41, then you have the inverter, charge controller, and DC to DC converter UL listing. So you're changing 1703 to 1741. If you change the first one into a 3 in UL 1741, you get UL 3741, which is the rapid shutdown listing. We call PV hazard control systems UL 3741 PVHCS. If you change the first digit in UL 1703 from a 1 to a 2, then you get the racking listing of UL 2703 for racks. If you change the first digit in UL 1703 from a 1 to a 4, then you get the listing for PV wire, which is UL 4703. If you change the first digit in UL 1703 from a 1 to a 6, then you get the listing for PV connectors, which is UL 6703. Whoa. For DG cable, you change the 17 in UL 1703 to a 30, then you get the DG cable, which is 3003 or 3003, we can say. As of December 2020, there became a new PV UL listing in town, which is UL 61730 rather than UL 1703. This is because the listing was harmonized with the Euro International listing, so the PV manufacturers no longer have to do 2 separate tests for a globally used PV module. All they did was add a 6 to the beginning of 1703, which is apparently some International Electrotechnical Commission, that's IEC, International Electrotechnical Commission thing. However, a 6 before UL 1703 was already taken by IEC 61703 mathematical expression for reliability, which is unrelated to PV. Darn those mathematical people competing with us for numbers. So the 0 and the 3 were transposed by some high-paid transposing expert, also known as a numerologist. And now we have the well-thought-out UL 61730 listing. If something is listed as UL 1703, you can still use it, but products first made after 2020 will do the UL 61730 test. Wow, that is a lot of numerology. Digest that. And so now we're done with the text box. 690.31C1, single conductor cable. Single conductor cable in exposed outdoor locations and PV-DC circuits within the array shall comply with 690.31C1A, B, and C. 690.31C1A. There are two wire types that you can choose from. 690.31C1A1, PV wire or cable, which has a non-standard diameter. So if you're doing conduit fill calculations, you have to get the wire dimensions from the manufacturer. So you can't just look it up in the NEC. And 690.31C1A2, dual listed as USE2/RHW2, which almost always is the case, as I mentioned before. And we have a discussion here. Dual listing USE2/RHW-2 was new in the 2020 National Electrical Code. Most USE2 wire already is dual listed as RHW-2, so it would be more difficult to find USE-2 wire that was not also RHW-2 wire. USE-2 wire on its own cannot go inside of conduit inside of a building, but when it is dual listed, it can go inside of a building on the coattails of RHW-2. The RHW designation includes the building wire fire rating required for conductors in buildings. PV wire also has the same fire designation and is usually also marked RHW-2. 690.31C1B. 8 AWG and smaller shall be supported every 24 inches. PV wire is permitted wherever RHW-2 is permitted, like in conduit. Exception for Article 691 large-scale PV electric supply stations, see page 171, where you can do various things that conflict with 690 with an engineered design. 691.4 defines 691 compliant, including requirement to be over 5 megawatts AC. For these large PV systems, you can secure at intervals determined by an engineer or engineers. Discussion. In the 2017 NEC and earlier, there was no 24-inch requirement, and we looked to 338.10B4B and 334.30, which let us support conductors every 4.5 feet. Some installers would like to have the distance be at least the width of a module, which is usually about 40 inches. But now it's 24 inches. Dang it! Dang it, dang it, dang it. 690.31C1C. Larger than 8 AWG shall be supported every 54 inches. This is new in the 2023 National Electrical Code. So that was 2020 NEC, 24 inches, and then 2023 NEC for large PV wires and things like that behind the array. We can go up to 54 inches, but who uses 8 gauge AWG behind their array? Use it in some places. Now here's another text box, USE2 and PV wire. USE2 cable and PV wire are the two most common wiring methods for connecting PV modules to each other and for connecting PV modules to anything else. These wiring methods are commonly installed under PV modules and do get exposed to sunlight. It is interesting that USE stands for Underground Service Entrance and has been tested for exposure to light. Not much sunlight underground unless you consider neutrinos sunlight. You know about neutrinos? Those things are weird. The -2 suffix is one way of indicating that something is 90 degrees C rated. In previous versions of the NEC, PV wire was specifically required for what was formerly known as ungrounded PV arrays in the 2014 NEC, but now there is no specific requirement to use PV wire. PV wire may be better than USE-2 wire and has been tested with more UV light, but USE-2 cable may be less expensive. When the PV industry was originally trying to get the code-making panel to accept ungrounded inverters, they used similar wiring methods to the systems with double insulation in Europe. PV wire is often the wire of choice of PV module manufacturers since it is acceptable everywhere in the world and with every version of the NEC. USE-2 cable and PV wire are often colored black and work better when colored black, since black is the color of carbon black, which is a pigment that helps with UV resistance by preventing UV light from penetrating. This is also why black cable ties are more UV resistant and why light skin can lead to deadly melanomas. When sourcing black cable ties, use nylon 6 cable ties when contacting everything except galvanized steel. Nylon 12 is necessary for any cable ties contacting galvanized steel. One last item for the cable ties. The NEC and UL standard require that the cable ties be rated type 21C. Were used for cable support. This type 21C designation will typically be printed on the package enclosing the ties. There was a time when some inspectors did not read 200.6 means of identifying grounded conductors, and they believed that white USE-2 cable was required. There are other ways of identification, such as marking. Some installers have used red USE-2 cable to indicate a positive conductor, and as the red faded, people would see white and think that the formerly red wire was a white grounded conductor. Oh no! Most, if not all, PV wire is also marked RHW-2 since it has to pass the same tests as RHW-2. The rating of RHW-2 allows the conductor to be installed inside of buildings. USA-2 without RHW-2 marking is not permitted because it may not have been tested for the necessary fire and sunlight ratings. 690.31C2 cable tray. There were some changes here and some jumping around. The NEC is required, such as jumping from Article 690 to 392 cable trays and 310 conductors for general wiring. In previous versions of 690, what was missing was what to do about conductors smaller than 1/0, that's 1/0, in cable trays, and then some wise guy, Dave Click, PE, pointed it out and caused us to make this book longer, which comes down to killing trees in the name of saving the planet. Dave, by the way, is a proofreader of this book, so if there are any mistakes, they are also his fault. Some Florida people. Not changed in the 2023 NEC were the following requirements. So we're talking about cable trays here. Support cables every 12 inches. Secure the cables every 54 inches. PV wire, PV cable, and DG cable without cable tray rating can go in cable tray outdoors. Now for the new rules, which apply to single conductor PV wire smaller than 1/0. So we've got some bullet points here. In uncovered cable trays, the adjustment factors for 1/0 and 392.80A2 are used. Article 392 cable trays, 392.80 ampacity of conductors, 392.80A ampacity of cables rated 2000 volts or less in cable trays, and 392.80A2 single conductor cables. 392.80A2 starts out not being specific to 1/0 and larger. It does tell us some important things that we should do when using cable trays, such as obey 310.14A2 selection of ampacity, which is where we select the lowest ampacity in a circuit unless that lower ampacity is 10 feet or 10% of the circuit length, whatever is less. This is a common wire sizing rule that you should be familiar with. See page 275. Do not obey 310.15C1 more than 3 current carrying conductors, which are familiar adjustment factors for greater than 3 current carrying conductors, which any wire sizing geek knows inside and out. Then 392.80A2 tells us that for our single conductor cables, or when our cables are cabled together, such as quadruplexed. Wow, I don't want to get a quadruplexed bypass on that one. Stressing out over that one. We need to follow A through D. 392.80A2A is for huge 600 kc mil and larger cables, and we are told to use 70% of the ampacities in 310.17 and 310.19. 392.80A2B is for 1/0 through 500 kc mils, and this is what 690.31C2 is referring to, and what we are mostly looking for, since we are supposed to use what 392.80A2B says for 1/0 cables, for cables smaller than 1/0. Note that C and D following also apply to 1/0. Now what it says here are two different things. Use 65% of ampacities in table 310.17 and 310.19. Use 60% if the cable trays are continuously covered and covers unventilated for 6 feet or more. Text box, tables 310.17 and 310.19. What we are mostly familiar with is table 310.17, ampacities of single insulated conductors in free air, which is based on 30 degrees C ambient temperature, and then using table 310.15B11, ambient temperature correction factors based on 30 degrees C to correct for hotter temperatures. The NEC does have tables based on 40 degrees C, such as 310.19, ampacities of single insulated conductors for free air, which is based on 40 degrees C. I have always been taught to ignore ampacity tables based on 40 degrees C. I recall someone on the Mike Holt team crossing out the page for a 40C ampacity table. We like to treat our NEC books as sacred and do not put marks on them, especially for NABCEP exams. So just use 310.17 for cable trays and use a special cable tray derating factor, which is probably going to be 65 or 60%. 392.80A2C is for 1/0 and larger. So we use it for smaller than 1/0 for PV. When single conductors are installed in cable tray with spaces between the cables that are not at least 1 cable diameter, there are no derating factors here, so you get 100%. 392.80A2D is for 1/0 and larger. So we use it for smaller than 1/0 for PV in these cases. If single conductors are installed in triangular or square configurations with free airspace in between them, at least 2.15 times the conductor diameter of the largest conductor, then there is no derating factor. So just 100%, just like we scored on our NABCEP exams, especially after reading this book. Now back from our detour to Article 392 and 310 and to 690.31C2, where it says, where single conductor PV wire smaller than 1/0 AWG is installed in ladder ventilated trough cable trays, the following 3 shall apply. 690.31C21, single conductors installed in 1 layer. 690.31C22, conductors bound in circuit pairs can be installed in other than a single layer. 690.31C23, sum of diameters of conductors shall not exceed cable tray width. And then we have figure 5.1, and it's just showing you different ways that circles, which represent conductors, can be stuck together with 1, 2, 3, and different configurations and flat and all that. It's so interesting to look at circles in geometry, especially the audio version. Figure 5.1 also relates to Chapter 9, Table 1, percent of cross-section of conduit and tubing for conductors and cables. It is all about geometry and where you can fit the circles. Summing up 690.31C2 cable trays. 1. We support our cables every 12 inches and secure them every 54 inches or less. 2. Instead of using Table 310.15C1 adjustment factors for more than 3 current carrying conductors when using cable trays, we find other rules and adjustment factors such as 65%, 60%, or 100% no factor in Article 392 cable trays, depending on the cooling effects of spacing and airflow. Now we have a text box. PV wire or cable and DG cable diameter. If you're looking for the diameter of your PV wire, take note that PV and DG wire cable has a non-standard diameter. It can vary from one manufacturer to the next. So we cannot use NEC, and we have to get the wire diameter from the manufacturer and use that along with Chapter 9, Tables 1, 4, and 5 for determining how many wires fit in conduit. PV and the NEC informational note. This quote above was an informational note in the 2020 NEC 690.31C2, which disappeared in the 2023 NEC, but still is good enough information for this book, which is really just one big and exciting 300-page informational note. Man, that's a lot of work. 690.31C3, multi-conductor jacketed cables. Although not defined in the NEC, a multi-conductor jacketed cable is simply a cable with multiple conductors in it that also has a jacket around the cable. A common example of a multi-conductor jacketed cable would be that yellow or white NMC cable, aka Romex, in the studs of your walls. You can also have DG cable and service entrance cables that fit that definition, or even your Ethernet cable going to a router or energy storage system. If said cables are part of a listed assembly, then install them according to the instructions. You always follow the instructions for listed equipment because that is how it was tested to be safe. Also, if something bad happens in the system and instructions are not followed, the lawyers will make a lot of money. Ouch. A microinverter cable is an example of this kind of cable that is part of a listed system. If the cables are not part of a listed assembly, then you can still install these multi-conductor jacketed cables in accordance with the cable's listing and in accordance with the following 1 through 2, A to F. 690.31C31, if on or in buildings, then in raceway. 690.31C32. If not in raceways, then A to F. And now we have A to F for 690.31C32, 690.31C32A. Marked sunlight resistant if exposed outdoors. 690.31C32B. Protected or guarded when exposed to damage. 690.31C32C. Closely follow the surface or support structure. 690.31C32D, secured no less than every 6 feet. 690.31C32E, secured no more than 24 inches from connectors or entering enclosures. 690.31C32F, marked direct burial if buried. To sum up multi-conductor jacketed cables, if it is inside, it needs to be in a raceway. And if it is outside, then it needs to be in a raceway or meet all 6 things above, A through F, or according to instructions if part of a listed PV assembly. 690.31C4, flexible cords and cables connected to tracking PV arrays. The following shall apply to flexible cords and cables connected to tracking PV arrays. We have some bullet points here. Identified as hard service cord or portable power cable, suitable for extra hard usage, listed for outdoor use, water resistant, sunlight resistant, stranded copper permitted to be connected to moving parts of tracking PV arrays in accordance with Table 690.31C4. And so let's talk about that table because sometimes it's a little bit confusing. Because some people will look at this table and not realize that this is only required for when you need flexible cords and cables connected to trackers, tracking PV arrays. And so this is also only going to apply to the part of the tracking array that is bending. So if you're connecting modules together that are on a tracking array that are not moving because they're all moving together, you don't apply it to that, of course, obviously. Apparently what happened was some people didn't use enough strands on some tracking arrays. You know, they move 365 days a year, 366 days a leap year. And in those cases, those wires broke. Dang. So we had to put it in the code. So 690.31c4 minimum PV wire strands only applies to tracking arrays where wires bend. And just for instance, a 10 gauge wire needs at least 19 strands, and there's a whole table that gives us these different numbers of strands. You'll also need to make sure when you have a certain amount of strands that you're using the right connector and terminal that works for the cable that has the strands. Now we're going back into some 690.31c4 flexible cords and cables connected to tracking PV arrays. Bullet points. Comply with Article 400 flexible cords and cables. And lastly, for bullet points, allowable ampacities in accordance with 400.5 ampacities for flexible cords and cables. Article 400 flexible cords and flexible cables discussion. Article 400 contains different tables to be used for flexible cords and cables, which are used for stationary conductors, including various ampacity tables, much like the Article 310 tables, but more flexible, as a pun, and 400.5 ampacities for flexible cords and flexible cables. Ha! Table 690.31c4 minimum PV wire strands discussion. Tracking arrays have moving parts that may bend wires back and forth 365 times per year, which can be 10,000 times or more in the life of a 30-year-old PV system. Wire with not enough strands will strain, harden, and break. Table 690.31c4 minimum PV wire strands does not have in its title that it is specific for tracking arrays, and if taken out of context, someone might think that it would apply with all PV wire on all PV system wiring. This table is only required for PV wire connected to moving parts of PV tracking arrays. For other types of wire connected to the tracking systems, you would look in Article 400, flexible cords and cables where PV wire is not covered. The ampacities in 400.5 and tables 400.5A1 and 400.5A2 differ from the ampacities typically used for conductors in free air in table 310.17. These cables also have different ampacities depending on how many conductors are contained within the cable. The ambient temperature correction factors in Table 310.15b11, formerly 310.15b1 in the 2020 NEC, or 310.15b2a in the 2017 NEC, do apply. It is interesting to note that Table 400.5A3 adjustment factors for more than 3 current carrying conductors in a flexible cord or flexible cable is exactly the same as Table 310.15C1 adjustment factors for more than 3 current carrying conductors. That's a waste of ink. Now we're doing it too. 690.31C5 flexible fine-stranded cables. Flexible fine-stranded cables shall only be terminated with lugs, devices, or connectors in accordance with 110.14 electrical connections. 110.14 electrical connections includes information on A, terminals, B, splices, and C, temperature limitations. In 110.14c, it says that conductors with temperature ratings higher than specified for terminations may be used for ampacity adjustment, correction, or both. This is something that is more of the complicated part of wire sizing. When you are correcting for ampacity with adjustment and correction factors, you do not take terminal temperatures or the 125% continuous current correction factor into consideration. You do not take the terminal temperature limits and the 125% required ampacity for continuous current into consideration without the adjustment and correction factors. You can read more about wire sizing in Chapter 12 of PV and the NEC to see how it is done in practice. And it is also covered somewhat when we discuss 690.8b. Just because something is in the NEC and you don't have to do it, it does not always mean that it has to make sense. Okay, take note, doesn't have to make sense. With some things, once you understand how it does not make sense, then you understand it. I could make a lot of analogies there, but I'm going to behave myself. Text box. Flexible fine-stranded cables, formerly known as 690.31H. Although 690.31H has moved to the cable section as 690.31C5, the NEC already has provisions for using proper terminations for the application in 110.14 electrical connections, but we are reminded about it here since many installers tend to forget this part of the code. Flexible fine-stranded cables shall be terminated only with terminals, lugs, devices, or connectors in accordance with 110.14. Flexible fine-stranded cables are easy to bend but are more difficult to terminate. Inexperienced installers in the past have used typical screw terminals that are not meant for flexible fine-stranded cables. In these cases, the connection will often become loose, resistance will rise, and heat will be generated, which can be a fire hazard. PV installers in the past used batteries and like to use flexible fine-stranded cables since they would not overstress battery terminals. Most battery cables now use flexible fine-stranded cables with the proper terminations. Batteries are no longer part of a PV system as of the 2017 NEC. PV arrays that track the sun do require flexible cables, and installers of these cables should be aware of the requirements for using proper terminal procedures and equipment. So that's the end of that text box. And by the way, if you're preparing for the PVIP NABCEP exam, you should know about flexible fine-stranded cables. Have that in my practice tests. Check it out. Heat spring, 690.31C6, small conductor cables. 16 American wire gauge, that's AWG, and 18 AWG single conductor cables are permitted for module interconnections if they, bullet points, meet ampacity requirements of 400.5 ampacities for flexible cords and cables. Other bullet point, comply with correction and adjustment factors from section 310.14, ampacities for conductors rated 0 to 2000 volts. 310.14 does point to the famous tables used for wire sizing in 310.15 among other things, such as 310.15B11 ambient temperature correction factors based on 30 degrees C and 310.15C1 adjustment factors for more than 3 current carrying conductors. Yep, podcast listeners out there, those are some important things to memorize because they keep changing them if you want to be a 2023 NEC geek. So that would be these tables for adjustment and correction factors. So it is now 310.15B11, which is where we find our ambient temperature correction factors. 310.15B11. That's the 2023 version. 310.15B11. Memorize that. And then for greater than 3 current carrying conductors and conduit, it is 310.15C1. So we put a C1 at the end for greater than 3 current carrying conductors and a B11 for ambient temperature correction factors. There you go. Flashcard that. Back to the book. Note that 310.14 does not direct you to tables 310.16 and 310.17, and instead we use the ampacity tables in Article 400 for flexible cords and cables, even though these small conductors are not necessarily rated as flexible cords or cables. Discussion. It may have been unthinkable to use 16 AWG or 18 AWG wire for PV systems when PV was more expensive. However, with the advent of falling prices, it is now thinkable and more likely in large projects using thin film modules with lower than typical crystalline silicon PV module current ratings. 310.10a, minimum size of conductors, says that we cannot use any copper conductor smaller than 14 AWG unless stated elsewhere in the code. 690.31C6 is officially elsewhere in the code. Did you know that a megawatt at a megavolt is 1 amp? Wow. 690.31D, direct current circuits on or in buildings. That's right, here it is. Direct current circuits on or in buildings. 690.31D. Wiring on or in buildings must comply with 690.31D1 and 690.31D2 below. 690.31D1 Metal raceways and enclosures, PV DC circuits inside of buildings. PV DC circuits inside a building that exceed 30 volts or 8 amps shall be inside of metal raceway, which is like EMT, Article 358 EMT, MC cable, Article 330, metal-clad cable, type MC. We are also directed to 250.1, 250.118, 250.118, 10, B, or C, which tells us how MC cables can be also used as an equipment grounding conductor. A couple bullet points here. 250.118, 10B, combined metallic sheath and uninsulated grounding conductor of interlocked metal tape of MC cable that is listed and identified as equipment grounding conductor EGC. 250.11810C, metal sheath or combined metallic sheath and EGC, combined metallic sheath and equipment grounding conductor of smooth corrugated tube type MC cable that is listed and identified as an equipment grounding conductor. Woo! 690.31D1, exception to metal raceways and enclosures, PVDC circuits inside of a building. This is a good one for all you rapid shutdown fans out there. That's right, rapid shutdowns. That was also the name of a band at the Solar Battle of the Bands. PV hazard control systems, that's PVHCS, in accordance with 690.12B21, which is UL 3741 listed PVHCS, see page 69, shall be permitted to use non-metallic or other than MC cables at the point of penetration of the building. Wow, so there's even an exception to metal raceways for PV DC circuits inside of a building, and that would have to have that 3741 listing. Text box. Things removed in the 2020 NEC to take note of. This inside of metal requirement used to be in the 2017 NEC and earlier and only applied up to the first readily accessible DC disconnect. This is no longer the case. DC parts of a PV system in a building require metal even after the first DC disconnect, unless part of a UL 3741 PV hazard control system. Also take note that the special requirements that were in the 2017 NEC regarding PV circuits embedded in building surfaces were removed in the 2020 NEC, perhaps due to 690.12, the roof is safer, and these requirements are no longer needed. Removed in the 2023 NEC were requirements for PV DC circuits in buildings that were using flexible wiring methods, such as FMC, that's flexible metallic conduit, and MC cable that required protection, such as guard strips. Yeah, we're doing away with guard strips. 690.31D2, marking and labeling. Photovoltaic power source or solar PV DC circuit. Unless located and arranged so that the purpose is evident, this wording above shall be marked on the following wiring methods and enclosures that contain PV system DC circuits on or in buildings. Not AC, only on or in buildings. So that means no inverter output circuits, no microinverters. We don't need the metal requirement for AC circuits. We don't have it for outside of buildings either. People always get confused about this. That's why I'm complaining. 690.31D2, marking and labeling. Photovoltaic source or solar PV DC circuit. Unless located and arranged so the purpose is evident, this wording shall be marked on the following wiring methods and enclosures that contain PV system DC circuits on or in buildings. Not AC, only on or in buildings. So we're talking about that red label that you're always seeing on the conduit. It's not required for AC circuits, and it's only required for DC circuits on or in buildings. Inspectors and installers always get this mixed up. So that's that label. We're actually working on the 2026 National Electrical Code. I'm on a labeling committee, and we might even get rid of that label altogether, or just require that it only says solar PV DC circuits so people aren't putting photovoltaic power source stickers on microinverter circuits, which is not required by the code. And now we're talking about this label requirement. 690.31 D21, exposed raceways, cable trays, and other wiring methods. 690.32 D22, covers or enclosures of pull and junction boxes. And 690.31 D23, conduit bodies with unused openings. Label shall be every 10 feet, every section separated by enclosures, walls, partitions, ceilings, and floors. This label specifications shall be capitalized, 3/8 inch height minimum, white letters, red background. Label shall be suitable for the environment used. Note, solar PV DC circuit is made up of fewer letters and takes up less space and resources, so it is better for the environment and helps save the planet. So I just say use solar PV DC circuit instead of photovoltaic power source, but both are acceptable according to the 2023 National Electrical Code. 690.31E, bipolar photovoltaic systems. Discussion. Bipolar PV systems have a benefit that voltage for the purpose of this code can be considered as being voltage to ground rather than the maximum voltage between any two conductors. Analogy. Your house in the U.S. is wired at 120-240 volt split phase. This means that you will not have more than 120 volts to ground in your house. However, you can have an electric dryer that gets all the benefits of 240 volts. This is because your house is bipolar in a way and is grounded and has a grounded conductor right in the middle of that 240 volts. A bipolar system has two monopole circuits, typically groups of strings, one positively grounded and the other negatively grounded. This type of system can potentially give the array 25% of the power losses, 75% savings due to voltage drop at double the voltage and half the current that it otherwise would have. The wiring rules with these systems state that we cannot have conductors next to each other that could have voltages greater than code allows for this wiring method and the conductors. If these conductors are in the same location, they need to be able to handle these bipolar hot-to-hot voltages that are double of what the voltage to ground can be. In other words, going bipolar does not give a designer the right to have two wires next to each other that have voltages greater than that for which they are rated. At the time of the writing of the 2023 NEC in this book, we did not see much in the way of bipolar systems. It is invigorating to think that we could have a 1500 volt to ground-mounted system that would have conductors that could measure 3000 volts to each other and still be NEC compliant. That could be efficient with the low relative currents. It is rumored that some bipolar plans may be in the works. Bipolar systems were much more popular just over a decade ago when the maximum system voltage for all PV systems was 600 volts rather than 1500 volts. 690.31F, wiring methods and mounting systems. Roof mounting of PV systems does not need to comply with 110.13. 110.13 mounting and cooling includes 110.13a mounting, and 110.13a says that equipment shall be firmly secured in place. Since many PV systems are ballasted and held in place by weight and aerodynamics, 690.31F is formally allowing ballasted systems. We are required by 690.31F to use an approved method to hold the PV and wiring methods in place and to design the wiring methods to allow for any expected movement. 690.31F informational note explains that expected movement is often included in structural calculations. 690.31G, over 1,000 volts, new in the 2023 NEC and referred to earlier all the way from 690.7 voltage and 690.12 rapid shutdown, is the ability to have circuits on a building over 1,000 volts. The reason this is here is because people want to have ground-mounted PV systems but still mount the inverters on the wall of the building. In order to have DC circuits over 1,000 volts on a building, we have to comply with all three of the following. 690.31G1, not permitted for 1 and 2 family dwellings. 690.31G2, not permitted for buildings with habitable rooms. Redundancy, since this would include 1 and 2 family dwellings. Got to change that in the next version of the NEC. 690.31G3, the following must apply. Exterior of building, 10 feet above grade. That's high as a basketball hoop, so only those who can dunk can get shocked. Kind of evens the playing field. Not greater than 33 feet along the building, which is the length of Sean and Bill's sailboat. It's a Ranger 33. After this 690.31 methods permitted marathon comes the brief. 690.32 component interconnections. This section is specific to building integrated PV systems. Fittings and connectors that are concealed at the time of on-site assembly and listed for such shall be permitted for interconnection of modules and permitted for interconnection of array components. Fittings and connectors shall be at least equal to the wiring method in insulation, temperature rise, and short circuit current rating. These fittings and connectors shall also be able to withstand the environment in which they are used. To repeat, Section 690.32 component interconnections was designed specifically for building integrated photovoltaic, that's BIPV systems, although it does not state this in the NEC, since BIPV, like microinverters, are not defined in the NEC. This is one reason why you need to read this book, to know these things. Otherwise, understanding 690.32 blindly would be totally confusing. 690.33 mating connectors. Connectors other than those covered in 690.32 component interconnections go here. These connectors are the primary connectors known to solar installers, including your typical MC4 connector or a microinverter cable connector. These connectors shall comply with all of 690.33A through D. The word mating was added to the title of this section in 2020. In the 2017 NEC, it was titled Connectors. This was to indicate what kind of connectors this section is specifying, since there are many other types of connectors in the electrical world. For example, spade connectors. 690.33A configuration. Mating connectors shall be polarized, example is positive or negative, but not both, or non-interchangeable with other receptacles of other systems. 690.33b guarding. Mating connectors shall guard persons against inadvertent contact with live parts. As you can see from playing with a typical MC4 connector, play with those things, you could not get your finger or tongue into the connector to touch metal. We have done this research, so do not try it at home. Whoops, don't play with these things. 690.33c type. Mating connectors shall be latching or locking. If readily accessible and over 30 volts DC or 15 volts AC, then they shall require a tool for opening. If mating connectors are not of the identical type and brand, then they shall be listed and identified for intermatability. It's a fancy word, intermatability, as described in the manufacturer's instructions. Discussion. We are not allowed to use MC4 connectors with Amphenol H4 connectors since they are not listed as intermatable. Although this was a common practice, here we see that there is a pathway for these different connectors to be used together. The process of intermatability is covered in UL 6703. Only 2 mating connectors currently used in the PV industry are intermatable. They are the Amphenol H4 and the Amphenol UTX. No other combination is officially intermatable. Any salesperson claim that is not backed up by an official UL 6703 certification is simply not true. Incidentally, how can you tell whether a salesman is lying? Their lips are moving. Ooh, hope we didn't offend anybody there. Buy this book. See, I'm doing some sales myself, but my lips aren't moving. 690.33d, interruption of circuit. Connectors shall be either one of the 3 following. 690.33d1, rated for interruption of current. 690.33d2, require a tool for opening and marked either do not disconnect under load or not for current interrupting. 690.33D3 supplied as part of listed equipment. 690.33D3 informational note. Equipment such as module level power electronics, including microinverters and DC to DC converters, are often listed so that the connectors can be a load break rated disconnect, even when the connectors say do not disconnect under load on the PV module connectors themselves. Wow. 690.34 access to boxes. Junction, pull, and outlet boxes used for wiring located behind PV modules shall be installed so that removing the module can make the wiring inaccessible. And that brings us to the end of NEC 690 Part 4 Wiring Methods and Materials, which is Chapter 5 in our book, PV in the NEC 3rd edition, based on the 2023 National Electrical Code. So if you want to find out more, you can go buy this book, check it out on Amazon, PV in the NEC. Make sure to get the 3rd edition, unless you want to learn about the 2020 NEC, which is the 2nd edition. And 2020 minus 3 years per NEC is the 2017 NEC is the 1st edition. We try to make the dry subject as not dry as possible. This is kind of a long podcast, so congratulations for making it to the end. If you want to find out more about classes, conferences that we're going to be teaching at, such as RE Plus in Vegas, you can find out more at Solar, SEAN, that's solarshawn.com. So thanks for listening to Shawn White's Solar and Energy Storage Podcast.